So coming back, let us now look into an actual example or a demonstration of how the flexure and the shear joint check is performed in RCDC. To start with, I have already imported a STAAD model in RCDC, and let us proceed ahead for the design settings and perform the ductile design for all the columns for this structure. As joint check is nothing but ductile designing and detailing of a joint, only if the perform ductile design option is selected, the joint check will be performed. Okay. Once my settings are made, I will quickly assign the load type to each load case which I want to use for designing. So just quickly assigning the type, selecting the load cases for designing, and I add the load combination for a regular type of a structure from the RCDC standard template and proceed ahead for auto design. Okay. So once the auto design is complete, we get a list of columns which has failed at any particular levels. Now the joint check report for all these columns which has failed even at a single intermediate level will not be generated. So joint check report is generated only for those columns which has passed throughout its extent in the structure. Now a separate report for joint checks is being generated for each column that has passed. So let us select column C1 for checking its joint check. So before proceeding ahead, let us quickly look into what is the geometry data or the section size of the column and which are the beams or what are the number of beams that are merging with the column at different levels and what are the direction or the location of the beams. So to see that, here is my STAAD model and this is the column number C1. So at each and every level, that is level 1, 2, 3, 4, there are 4 levels. There are 2 beams which are framing into the column to form a column beam joint. So there is a beam at 0 degree and there is a beam at 270 degrees. Now all this data will be imported in RCDC also. Coming back to RCDC, the first thing that has been calculated is the moment capacity of the beams that are framing into that particular joint. So for ease of understanding, which is the critical combination with from where this forces or the critical load combination is identified, what I have done is I have designed the beams at this level, which is 4.2 meter level. And if I generate the detailed calculation report of this beam at 270 degrees, I can simply check the critical load combination for my right sections. So for my top reinforcement, the critical load combination is 90 and for my bottom reinforcement, the critical load combination is 22. So if I check that the critical moment is 470.35, which is the same which is being considered while performing the joint check also. And for the bottom, it is 300.36. So once these moments are being determined or being read from the model data, a local algorithm calculates the AST requirement of the beam and actually details the top and bottom reinforcement of the beam to suffice the AST requirement. So for a moment of 446 or say 470, the AST requirement is calculated and the beam is actually internally detailed for what should be the top reinforcement and what should be the bottom reinforcement, and then a final value of AST provided is being calculated. Now from this AST provided calculation, the MU capacity is being determined. Moment capacity of each beam separately for top and bottom is determined, and then the resultant moment for both the directions, that is along column B and along column B, is identified. So once we arrive at a stage where the final resultant moment of each beam along both the directions is determined, we then do a combination of sway left and sway right to find out the total maximum capacity in the beam required. So in this case, we have one beam along each direction. So along D, we have a beam on the right hand side, and along B, we have a beam on the left hand side. So if we just quickly look at the case where there are beams on all the four sides. So let us take an example of column C7. Let me check the joint check report of column C7. So if we come here, we have beams on all the four sides, 0, 90, 180 and 270. So in this case, once the final resultant moments are determined, when we come for a combination of sway left and sway right, these moments get added. Like if we look at this image, considering this as a column with beams, each beam on one direction, then what we do under the sway left, sway right condition for getting the maximum capacity is we add the sagging and the hogging moments on the diagonally opposite sides of the column. So coming back here, the moment capacity of the beam is nothing but the addition of left bottom right top and or left top right bottom. The maximum of both of these combination is considered as the moment capacity along each direction. So this is how we actually arrive at a value of the moment capacity of beam. Okay, so now coming on how the flexural capacity of the column is actually calculated. Now, as we are currently into the IS 13920-2016 code for performing the joint checks, there are two different options that are available. That is, we can perform the joint check for P maximum, or there is another option for performing the joint check with all the load combinations. So currently we have selected the option to perform the joint check for all the load combinations. So let us first look at how the calculation happens for the option of all load combinations. So when we select that option, there are two reports that are generated. One is the regular joint check design report, where the details are provided and column flexural capacity is presented for a critical load combination. But under the all load combination report, if we come to the check of column flexural capacity, we can see that the capacity of column for all load combinations that consist of earthquake load case is calculated. So all this load combination from load combination 2 to 13. So if we just quickly look at the load combinations, my first load combination is purely a gravity combination, whereas all the other combinations has either earthquake X or earthquake Y as a load case in that. So all these load combinations with earthquake component are filtered, and for each combination the ratio of MNC upon MNB is calculated. And first check that is done is that the ratio should be less than 1.4 in case of IS code. So in this case, the first check that is done is the ratio has to be more than 1.4. Secondly, what happens is for all the load combination, what the program does is it checks which is the combination with the lowest ratio. So in this case, for the column C1 and the joint at 4.2 meter level, the combination number 12 has the ratio of 3.05 along the column D, which is the least among all the other combinations. So this combination is considered as the critical combination, whereas direction of column along D, the ratio of 1.86 is found out to be the lowest ratio, and hence for this direction as well, the combination that has turned out to be critical is 12. So now when we check both these reports, that is the joint design check report and the all load combination report, by keeping them side to side. So now for the direction which is along the column D, if we check, my critical load combination number is 12, which is this, and my PU at top is 559.75, and its corresponding capacity is 805.83. Similarly, for the bottom, the PU is 601.49 and its corresponding capacity is 655.79. So in this way, the column capacity for each load combination is being calculated. Now this moment capacity for the column that is calculated is actually done by using the TM interaction curve, which is being plotted for each and every column along both the directions, that is along the major and the minor direction of the column, and for all the load combinations. So just to make it simpler in understanding, let us assume that this is our column C1, which is starting from the base level and is present on 4.2, 7.8 up to 16 meter of level. Now we are calculating the moment capacity of this particular joint for this column. Okay, so the column from base to 4.2 meter level, the top moment capacity of this column will contribute in this joint, and similarly the column between 4.2 to 7.8 will contribute, the bottom location of this column will contribute to the moment capacity of this joint. So what we need to check is the moment capacity of the top location of the column below the joint and the moment capacity of the bottom location of the column which is above the joint. So first what we do is we check the moment capacity of C1 between 0 to 4.2. So coming back, the C1 between 0 to 4.2, right click, and when we go to interaction surface, we need to check the top joint of this column. So for load combination number 12, if I check the top joint, the P is 601.49 and the corresponding moment capacity along the X direction is 656 and along the Y other direction is 433. So when we come back to the report, this is our actual report. So for column combination at top, the PU at top above, which this means that it is above the joint, and critical load combination for the column below the joint, which is the bottom location. So the PU on the bottom of the joint is 601.49, which we currently saw, and its corresponding capacities in X and Y direction are 656 and 433, which is 655.79 and 433. So similarly, we can check the moment capacity of the column above the joint. So coming back to our RCDC environment, I will check the moment capacity of the bottom location of this column. So coming back here, inside the interaction surface, for the same load combination which is 12, but this time for the bottom location. So for the bottom location, the PU is 559.75 and the corresponding X and Y capacities are 806 and 530. So when we come back to the report, for PU at the top location, that is above the joint, as we are referring and doing all the calculations for joint, the top and bottom will refer to the top above joint and bottom below the joint. So the PU for the top of the joint is 559 and its corresponding capacities are 806 and 530, which we currently saw. So in this way, the moment capacity of the column is being calculated. Now going back to the joint check report for column C1. Once the beam capacity and the moment capacity is finalized, we check the ratio whether the moment capacity of column divided by the moment capacity of the beam is greater than 1.4 or not. As we are already known that the column design and the joint check goes parallelly. It does not happen that the design is performed and then with the design the joint check is being done. No. So whenever there is a failure of the joint flexure check, what happens is RCDC tries to either increase the reinforcement up to a maximum possible limit, taking into consideration the detailing criteria as well, and tries to suffice the flexural joint requirement of the particular joint. So that was about the flexural joint check for the column beam joint. Now coming to the shear strength of the joints. Under the joint shear check report, the first table represents the beam data, which is the number of the beams that are present along each direction, that is independently along the direction D and along B. The second table represents what is the AST total required by considering the sway left and sway right condition for arriving at the AST total required, that is the AST provided total for the sway left, sway right condition. The next value under this table is the calculation of V reinforcement. So V reinforcement is nothing but 25% more the strength of the steel, and we arrive at a value of V reinforcement. The next term is max of VUY1 and VUY2. So these VUY1 and VUY2 is nothing but the beam shear, that is the shear that is induced due to the beam at a particular joint. So let us check how these values are arrived up to. So when we generate the design calculation report for column C1 at level 4.2 meters and directly jump over to the shear design part, the calculation of beam shear due to the sway condition again, that is the sway at right and sway at left, is determined for both the directions, that is VU1 and VU2. And what we take is max of VU1 and VU2 for each direction. So along D and along B, we get a maximum value for each direction. So when we come back to our joint check report, we see that a max value of VU1 and VU2 is considered for D, and separately the same value is being considered along B. So once the actual shear in the joint is determined, we need to determine what is the shear demand in the joint. So shear demand is nothing but the V reinforcement minus we deduct the actual shear on the joint. Once we get the shear demand in kilonewtons, we need to determine the area of the joint. So the width of the joint is calculated as per the codal provision, wherein the code says to calculate the width of the joint as the minimum of both these values, that is the width of the beam framing plus the depth of the column, or it should be width of the beam plus 2 times the factor x. So in this case, for us, the value of width of the beam plus 2x is going to be the minimum one. I have shown the calculation of this particular value, which turns out to be 600 mm. And so this is the area of the joint. The next value, that is the tau JD, is nothing but the shear demand of the joint. The actual shear demand divided by the area of the joint, which has to be less than the nominal shear strength of the joint. Now nominal shear strength is a factor into the square root of f dash c, and this factor is dependent upon the confinement of the joints. So in this way, the shear strength of the joint is calculated. Now the shear strength of the joint has to be greater than the actual shear strength. In case when it is the reverse, the joint fails for the joint shear check, and to make a joint pass for that check, we either need to increase the concrete grade or we need to increase the size cross section area of the column. So that's all about how the joint check for the shear is being performed in RCDC.